going to start by trying to convince you that what we're building is pretty general and can do a lot of stuff. How about that? Okay, so let's start at the very basics. What is intelligence? We've kind of talked briefly about this, sort of. A little bit more in my AI class. But what do you think it is? Variety of situations. Okay, I just grabbed some adjectives you used here, or some words. What do you think? You agree? Is that what intelligence is? I've heard somebody define it as the ability to operate effectively under diverse conditions. Sound good? Rationality. Okay. What is rational? Everything that agrees with my rational thinking, right? And everything that disagrees with it is irrational?
Rational means that you live by the rules of logic.
Logical, okay, logic, stuff like that. Yeah, at some point, intelligence needs to result in decisions, or else you've got intelligence in a vacuum, right? I mean, what good is intelligence if it has no body, if it's just intelligence floating in space? Is that intelligence? Well, maybe it is intelligence, but it's not any good, right? It's kind of worthless. Okay, as soon as this intelligence is able to do something, make decisions, then all of a sudden it becomes an intelligent being, or a intelligent robot, or an intelligent... I'm going to claim intelligence has to be able to make decisions, and decisions have to actually do something. Don't you agree with that? Yeah, so I think we all agree knowledge is a pretty important part of it. If you have no knowledge and you're making decisions and they're turning out good, you're just getting lucky, right? So somehow we have to use that knowledge to make good decisions that do something good. Now, whether those decisions are part of intelligence, I think is debatable. I kind of feel like they're not. I think intelligence is making the decisions, and then doing them is why you have intelligence in the first place. Sound good? Okay. By the way, definitions like these, I'm not going to be testing you on them because I don't think the world knows the answer. I'm just trying to get you to think about it so we can reason about intelligence a little bit. If you are really good at doing arithmetic, but you can't do anything else, are you intelligent? Intelligent in that small area. Kind of when we say intelligent, we mean general, right? So we got this one. You kind of need to be able to handle a lot of conditions and use your knowledge and to make good choices, and yeah, I'll just circle the whole thing there. So if you do all that stuff, you're intelligent, right? Okay. Do we even know that intelligence is possible? What if the universe is so random that it doesn't really matter what you do? Do your choices matter? I think they do, because people that smoke get lung cancer and people that don't are less likely to get lung cancer, right? And I should have said are more likely to get lung cancer for people that smoke, because not all people that smoke get lung cancer. People that go to school usually make more money than people that don't go to school. Is that necessarily true? I bet you if you did the statistics, I bet you Bill Gates and a few others alone would tip the balance so far that it would look like it's better not to go to school. So is averaging a reasonable way to, well, I think he did go to school but didn't complete it. So maybe it's best not to complete education, right? Did Zuckerberg complete his college degree? No? Okay. Yeah, see, I'm pretty sure at some point the scales are tipped. It's best to drop out of college. And yet we all know that's not right because we're intelligent, right? Okay. So where am I going with this? I guess what I'm trying to say is this: do your decisions really matter? Let's just assume they do, because if they don't, then intelligence is futile and we're wasting our time in this class. So by virtue of necessity, I'm going to say intelligence matters. There is determinism in this world. Things actually matter. I'm going to claim that's a good assumption because consider two universes. This universe is mostly observable, but there's a hidden variable as represented by this black box over here. So you are a being that lives in this universe and you can see what's going on, but there's some things you cannot see, and those things you cannot see affect the world around you. Now imagine you live in this universe. I don't even know why I'm drawing circles. This isn't helping at all. There are no hidden variables. You can see everything, but the universe operates with non-determinism, meaning it's impossible to predict what's going to happen next because things happen according to magic. Is there a difference?
Yep.
Okay, what's the difference?
Stability.
Stability. Patterns?
That you can
Okay.
predict.
Well, we can't, there might be patterns in this one. I'm just not saying there are.
Well,
I don't know.
so they're the same then, I guess, because
Yeah, I guess. Yeah, so we're sort of playing guess what the professor is thinking game. Here's what I'm trying to get at. I claim that a deterministic universe in which there are hidden variables is indistinguishable from a non-deterministic universe. Is that fair? Or in fact, non-determinism really is hidden variables. Maybe we're non-deterministic because there's something we can't reach or touch or feel or understand in this universe. Or maybe there's just stuff we haven't yet reached or touched or felt or measured. I guess I'm not expressing very well. There's also a difference between, is there consistency in patterns and rules, or is there entirely lack thereof? Is the world chaotic and random, or is the world sort of organized and consistent? And if it's organized and consistent, then remembering patterns and making predictions is going to lead to intelligence, right? Whereas if you live in black, white noise, right? Everything's just chaotic and random and there's no patterns at all. Is intelligence even possible? I claim it's not. Okay, so I like to pretend the world is totally deterministic, but there are some hidden variables. I think that describes our universe pretty well because it suggests that there are patterns to everything, we just might not know what they are. It suggests that if we know more, we can be more intelligent and have more patterns, and it suggests that ultimately everything can be known, it's just we don't know it all necessarily yet. So is that really accurate? I don't know, but if we do live in one of these non-deterministic universes, well, I don't think we'll ever know that because I think this is indistinguishable from one in which there's just something we haven't yet measured. Okay, that's really theoretical. Now let's try to bring it down to earth a little bit more. Let's see. So we live in a world that's continuous, right? So how many moments in time are there?
all of them.
All of them? Okay. Unless you get down to the Planck constant, and then we run that through the E equals mc squared to figure out the tiniest unit of time. And then we ask ourselves, are we living in a simulation? And then our heads blow up and things like that. Is time continuous? I guess as far as we know, unless there's some physicists that know better. If it's not, it's discretized at a darn granular level, right? What about space? Is space continuous or quantized? It's quantized? Dang it, that's so non-intuitive. I hate that.
Talking to physicists here.
Okay, so it's quantized, but it's quantized at a tiny little level, right?
Yeah, so to a great approximation, everything's continuous.
Okay, well that actually helps my argument a little better. Next I want to say, if we discretize our model of the universe, can it be accurate?
Yeah.
So here's my point. If we discretize at a fine enough granularity, it's going to be close enough. Don't you agree? So suppose we represent the universe as a finite set of states. These are no longer universes, now they're states. Here's the number of states in the universe, and if you want, you can transition from this state to that state, and then from this state to that state, and then from this state to that state, or to that one, or back to yourself, or maybe you go to that one, and from here you can go to that state. And this model is obviously not sufficient to represent the world. There's more than 6 states in the world. There might be infinity if it's continuous. Who knows if we're quantized? Maybe we look like we're quantized, but then if you get down close enough, it turns out that they're kind of like clock cycles in a CPU. You know how you make a square wave, but then if you look at it close enough, it has rounded corners, and it turns out it's actually continuous, approximating discrete. So maybe the universe is quantized, but really it's continuous, and then maybe it's even discrete underneath the continuous level, right? Do we know? No, because physics is so tiny. But if we built a big enough one of these, big state machine, could that represent the universe?
Yep.
In theory?
If
If we had enough states, we're in theory now, this is utterly impractical, you couldn't do it in a machine, but if you had enough states, and if you discretize time at a small enough granularity, presumably this could accurately represent the universe, I claim, something like that. Okay, so how long do you have to remember? I'll circle that because we wrote the word once before. How long do you have to remember in order to be intelligent?
not very long.
Not very long?
Long enough to make decisions.
Yeah, I guess as long as it matters, right? If you can remember prehistoric times, that's not going to help you predict the stock market better because stocks themselves have only been around for a few hundred years, right? Okay. So I think there's a limit in time to the value of memory, maybe. Here's an interesting thing. Let's suppose that we discretized states are sufficient to represent the universe. And let's suppose you have to remember 2 time steps ago in order to accurately predict everything that happens. Now, this is not the real universe. This is a hypothetical game universe, right? But in this game, if you have a memory of size 2, you can perfectly play the game. You with me? What if now, in every state, there are at most, 6 things I could remember, because I could have been in any of these 6 states 1 time step ago, and then I could have been in any of the 6 before that 2 time steps ago. So there's only 36 possibilities in each state, right? So what if I multiplied each state into 36 separate states and build a great big state machine in which the state itself represented my memory of 2 time steps ago? Does that make sense? What I'm suggesting here is, in theory, if I expand my state space, I can decrease the necessity of memory. Follow the reasoning? Okay. The argument here is there's something called a k-order Markov model. And historically, there was first a Markov model. A Markov model is a model in which you have no memory, but except for you have this concept of state. And you transition from state to state to state, and that is the model of the universe. So this thing I've drawn up here is a type of Markov model. This is actually called a Markov decision process. A Markov decision process. So the difference is a Markov model models the universe as going from state to state to state. A Markov decision process does the same thing, but it assumes you get to make choices. There's decisions in here. Most games are Markov decision processes because when you're in this state, you get to choose if you go to this state or that state. And of course, somebody else is making choices too, and so there's probably some degree of control that you have and some degree of control that you don't have. In the pole cart game, you can just will the pole to stand upright, but not going to happen. You don't have that choice, right? But you can choose whether to move the cart left or right, and that's going to also affect how gravity affects the pole, and so you have some decision power, but not total decision power. All right. So a Markov model is used for just sitting back and observing the universe and predicting what's going to happen next. Markov decision processes are for predicting the universe while assuming you make decisions. So I'm going to go like that. A k-order Markov decision process is a generalization of a Markov decision process where we assume that you have to remember the previous k states in order to operate effectively. And I'm going to claim that any k-order Markov decision process can be reduced to a k-1 order Markov decision process by multiplying the size of the state space. Do you follow that? If we use different states for every possible thing you could remember, and this of course assumes you have discretized memory, but now we can recursively say, hey, we can do away with k-order Markov processes and we can model the entire universe as a Markov decision process, in theory, It's not necessarily practical. But given that we have an arbitrarily large number of states, we don't really even need memory anymore. We just need to know what state we're in, which kind of is a stub for memory. And now this can accurately represent the universe.